Okay, this is a problem that we've actually come across that can be a really complicated solution, but we can actually make it into an easier solution by doing a lot of algebra. Okay, so we're going to calculate range, okay, and range is just a fancy term for x distance, okay, without knowing time. Right now, the only equation we have to calculate x distance is v initial x times time. We have to know time in order to calculate this x distance. What we want to be able to do is calculate the x distance without time. So I'm going to show you a way to do that, okay, just knowing a few other things, okay. So what we are going to know, and what you have to know, is we do have to know what the initial velocity is, and we do have to know what the launch angle is, okay? Other than that, if we do some algebra, we can actually calculate how far an object is going to travel. So, okay, what we're basically looking for is, okay, the distance that an object will travel, only knowing the angle and the initial velocity. So there are a lot of factors that go into this, okay? And you have to think about, okay, what do I know and what can I find out? So the first thing, obviously, is we want the x direction equation, and we're going to use x equals v initial x times time. Now, something we're not used to, but we're going to have to get used to it, is every once in a while we need to put in what v initial x is. So v initial x right here is really v initial times the cosine of theta times time, and we're going to have to use that. Okay? And we can't go anywhere with this particular problem because we essentially have two unknowns. I don't know time and I don't know x. If I have two unknowns, I can't solve the problem. So then you think, okay, what are some of my y direction equations that we could use? And one of the y direction equations we can use is y equals v initial y t plus 1/2 g t squared. Now, one of the reasons why we can use this particular equation is because if I start and end at the exact same point, then y equals 0. And that is one of the keys for this particular problem. So I can say y equals 0, and then I can bring this term to the other side of the equation, and I have v initial y t would equal 1/2 g t squared. And you are correct. I need a negative there. Okay. Now, I'm going to do some fancy things here. I'm going to get rid of t by dividing both sides by t. And I also know that gravity is negative, and I have a negative here. So because those two I know are going to be negative, I'm going to drop the negative sign right now. Okay, so right now my t goes away and that t goes away. And so I end up with v initial y equals 1/2 g t. Okay, now as we go here, I still essentially have two unknowns. Okay, because I don't know what time is. Okay, but I do actually kind of know this. But I'm going to do something here. V initial y is really v initial times the sine of theta. So we're going to plug that in here. So v initial sine of theta equals 1/2 g t squared. Okay, now you may not think we're getting anywhere here, but we really kind of are. Here's the deal. Okay, oops, sorry. Hopefully you caught that. I got rid of that squared a long time ago. Okay, so you may not think we're getting anywhere, but here is where we are getting. This time right here and this time right there have to be the exact same time. Okay? If I have an object that is starting here and going through the air and ending there, the time that it takes to go up and come down has to be the same as the time that it takes to go across. So those two times are equal to each other. Okay, and so there's a couple of ways to go about this particular maneuver, but what I'm going to do is I'm actually going to solve both equations. Well, actually, no, I'm not. Okay, what I'm going to do is I'm going to solve this equation right here for time. Okay, so when I do that, then I have to multiply both sides by 2. That gets rid of my 1/2, and I have to divide both sides by g. So what I have here is time equals 2 v initial sine theta divided by g. And if I go back up here, and I will bring this equation down, so what I have is my x equation equals x equals v initial cosine theta times time. Since this time and this time are the exact same, okay, I am going to take this whole mathematical term and I'm going to plug it into that. So now what I will have when I do that, let me get through some writing space here, is x equals v initial cosine theta. Now I'm going to write this in red, times 2 v initial sine theta all over g. Okay, so I just put that term in for time. That's all we did. Okay, so now I'm just going to kind of rewrite this, where x is, I'm going to bring this 2 out in front. Oh, actually, no, I'm not. Sorry. I am going to bring, or I'm going to take v initial times v initial. So I'm going to get v initial squared times 2 times the cosine of theta times the sine of theta, all divided by g. Okay, and here's where it pays attention, or does you good to pay attention in math class. And I would not expect you to know this. We could actually put this equation on our note cards as it is, but this right here is actually a trig function. So 2 cosine theta sine theta actually equals the sine of 2 theta. Okay, this is a trig thing. Don't really expect you to know that. But what I can do is shorten this equation up by replacing all of that with that. So now my x equals v initial squared times the sine of 2 theta all over g. And this right here is called the range equation. You should put that on your note card, but what that tells you is it's going to give you x distance, and if you look inside here, I don't need to know what the time is. All I need to know is what is the initial velocity and what's the initial angle, and I can find out what the distance that an object will travel is. Okay, so let's use this on an example problem. So a motorcycle is going to jump a ramp at an angle of 30 degrees at a speed of 45 miles per hour. And what we want to do is we want to find out how far away should a second landing ramp be placed. So this motorcycle is going to go up over the ramp and come down and land on that ramp. What we are interested in is what is that distance. Notice all we are given is theta is 30 degrees, and V initial is 20 meters per second. I'm not given any time. Okay, so we could do the old trick of finding time in the y direction and substituting it, but we now have a nice, neat little equation that says the range x is V initial squared times the sine of 2 theta divided by g. Okay, so if I plug everything in here, I'm going to have 20 squared times the sine. Now this 2 theta is what gets everybody. It's 2 times 30 is all that is, okay? So essentially this becomes the sine of 60 divided by 9.8 meters per second squared. And if you do that, we can find out how far it goes. So x would be 35.3 meters. And if we do a unit check, okay, our units here, right here, our units are meters per second squared, and that's all you have for units on top, all over meters per second squared on the bottom. And so you have a meter squared per second squared all over a meter per second squared. Seconds cancel, one of those cancel, and lo and behold, we get the right units. Okay?